Okay, good evening, everybody. Let's start today's discussion. Am I audible?
Yes, sir.
Okay. Is my screen visible?
Yes, sir.
Okay. Okay, so today our first question is in which of the following compound following the tertiary butyl group will most likely to occupy the axial position in the most stable conformer? So, how can we solve it? We have to usually we know that the tertiary butyl group is a anchoring group and it usually keeps itself to the equatorial position to minimize the steric interaction, right? So here we can see that in place of carbon we have the two oxygen atom in the 1,3 position. So let's draw the structure of the C. So in the chair conformation, okay, so this is the structure of the C. So as we can see that here in the axial CME3 group is in the axial position, and here in the as you can see that in the 1,3 diaxial interaction, that is in the normal cyclohexane structure, a normal hydrogen is there. If there is carbon atom in place of oxygen, so there is another hydrogen atom is usually there. So there is a steric interaction between these two groups, right? But in case of the oxygen, there is no such interaction is possible, right? So in case here, as here no hydrogen atom is there, as this is oxygen atom, so there is no 1,3 diaxial interaction between them. That is why the tertiary butyl group keeps itself in the axial position as there is no 1,3 diaxial interaction. So here it is in the axial position. Okay, and in case of structure B, as you can see, this is similar kind of structure, but here methyl is there, and the positions of the oxygen is reversed. Means it is situated in the 1,3 position with respect to the methyl group, but as tertiary butyl group is much bulkier than the methyl group, so the option C. In case of option C, the tertiary butyl group will keep it in the axial group and it is the stable conformation. Okay, any doubt? Any doubt, anybody? Okay, so let's move to the next question. Okay, so can you tell the answer of this question? This is already discussed earlier weeks. Anybody? Hello? Anybody? So let's discuss. As you can see that in case of B and C, in case of option B and C, the tertiary butyl groups are there, right? They are the very bulky groups, tertiary butyl groups are there. And which isomer is this? B, cis or trans? Hello? Hello? Okay, so this is cis isomer. As the two, as you can see, here is one hydrogen, and you can see here hydrogen is there. So the two tertiary butyl group are toward the downward, toward the same side. So this is the cis conformation, and this is the trans conformation, right? The two tertiary butyl group are in the opposite direction. Okay, so let's draw the. This is in case of the cis isomer of this 1,4 tertiary butyl cyclohexane. To minimize the syn 1,3 diaxial interaction, it exists in the twist boat conformation. Okay, as you can see that a tertiary butyl group is always in the axial position. Okay, so there is some 1,3 diaxial interaction between the hydrogen atoms of these groups. So it is to minimize that, it keeps it in the twist boat conformation. So here hydrogen is there. Okay, so in case of the cis isomer, to minimize the 1,3 diaxial interaction, it exists as the twist boat conformation. But in case of this isomer, trans isomer, as you can see in the inverted structure, the both tertiary butyl group it can be situate themselves in the equatorial position. So there is no 1,3 diaxial interaction in case of the trans isomer, which is possible in the cis isomer, as there is one axial tertiary butyl. So the 1,3 syn diaxial interaction is possible with the neighboring hydrogen. Okay, there is a hydrogen, there is hydrogen. So there is maybe a possible interaction. Any doubt? Anybody? Hello? Am I audible?
Yes, sir, you are audible. You can proceed ahead.
Okay. Okay, so coming to the next question. Which of the following statement is correct regarding the Z methyl cyclohexyl diene acetic acid? So as here is a double bond is there, so it can, there is one hydrogen, so it can exist as the cis or the trans isomer, right? So our concern is with the Z isomer. Okay, so Z isomer can exist in the following two conformation. This is Z isomer, as you can see that the higher priority group of this carbon, that is COOH, and of this carbon is of the this side, as this is more substituted one. They are on the same side. Now the question comes from the this carbon atom. Okay, so it is methyl group can be either axial, this one, or equatorial position. So now tell me which one is more sterically stable, the methyl group in the cis, sorry, methyl group in the axial or methyl group in the equatorial? Any idea?
Methyl group in the eggshell will be more stable.
Exactly. As in the equatorial conformation, there is a steric interaction between the COOH and the methyl group. Okay, so in case of the axial methyl, they are far apart from the each other, so there is less steric interaction between these two groups. So this is why the methyl group in the axial position is more stable due to the existence of the axial 1,3 strength. So option A is the right option. Okay, any doubt?
No, sir.
Okay. Okay, let's move to the question 4. Tell me which is the correct answer in option 4. This is a menthone, right? As in cyclohexane, C double bond O carbonyl group is there. So this is the structure of menthone. This is called menthone. Okay, so let's draw the structure of both di-equatorial and di-axial form. Carbonyl group is here. We are placing this is what form? Di-equatorial or di-axial? So tell me, this is
First one will be di-equatorial.
exactly in first one, both methyl and the CHMe2 both are in the equatorial form. So this is di-equatorial form. And in second case, there is diaxial. Both are in the axial. So this is the diaxial form. Okay. So in case of the option 1, this is di-equatorial form. both 1 2 and 1 3 uh, alkyl ketone effect cooperate each other to stabilize the diaxial. Here is a destabilizing structure, as in case of the carbonyl group. When a carbonyl group is there in the cyclohexane, so the energy difference between the axial and the equatorial is decreased with respect to the normal cyclohexane. This is called the 2 alkyl ketone effect. And in case of the this is called, as you can see that here, this is in case of the 3 alkyl ketone effect, here methyl group is in the axial position, but in case of the normal cyclohexane there would be a hydrogen, but here hydrogen is missing, so there is no 1,3 diaxial interaction. So in this case also, the energy gap separating the axial and the equatorial is decreased with respect to the normal cyclohexane. This is called the 3 alkyl ketone effect. So in case of the axial form, the both effect cooperate to each other, as due to the 3 axial ketone effect, it is stabilized at in the 3, as in the 3 position. There is no hydrogen is there, so there is no interaction. And in with respect to the 2 alkyl ketone effect also, the axial substituent in the 2 position is also stabilized. Okay, so option D is the correct option. Okay, so now this is, there are two sets of compounds are given, and we have to predict which have the lowest pK value. So do you know what is the correlation between the pK and the acidity? What do we know? The more acidic the compound it is more less pK value or more pK value it has? If you are
More
thinking,
as yeah.
yes, anybody, please. Anybody can say. Anybody wants to say something?
Yes, sir. More acidic the compound is, less will be the pK value.
Exactly. The more acidic the compound, it has the less pK value. So let's start with the set one, means pair A. Let's discuss. Okay, so at first we will draw the structure of the compound one. Okay. Okay. Is this correct? Can you see it? It is a little bit outskirt from the slide. Can you see it?
Yes, sir.
Okay. So this is monoanion form, right? And this is dianion. It has released the hydrogen ion, and it has become the O minus carboxy group. Okay, so this is the measure of the acidity. We know that with the more ease a compound releases the proton, it is more acidic, right? So let's draw the structure of the two. So now you tell me, I have drawn the possible structure of this is the 1 and this is the 2. Now you tell me in which case which is supposed to be more acidic, which compound. Here you can see that the both are in the axial position, so they are far apart from each other. But in case of the 2, they are they both are in the equatorial conformation, so they can form a hydrogen bond, and the dianion form is are although in the equatorial form. So now tell me any clue or anything you can predict from here, from the drawn structure, that which one can be more acidic, 1 or 2? For 1 it is more easy to release hydrogen, or for 2?
So I think for the first one, it will be more easier to release hydrogen.
Exactly. From the first one, it is more easier because there is no hydrogen bonding is present. As in case of 2, a stable intramolecular hydrogen bond is present between the carboxyl O minus and the hydrogen atom, right? So this hydrogen will never supposed to get released, and this will be very difficult to form the dianion form, right?
Yes, sir.
So this is more acidic. Okay. Now, in case of the pair B, the same we can discuss the answer like the same way. Let's draw. So here NH3 positive is there, and here hydrogen is there. But in one case, OMe is in the same site, and in another case, OMe is in the equatorial position. So now tell me, with the connection to the first problem, can you see any kind of similarity between these structures depending on the intermolecular hydrogen bonding? In which structure hydrogen bonding is possible?
In the first one.
Yes, in the first one. So in case of the 3, methoxy oxygen is there, and there is also NH3 plus. So with one of the hydrogen, there may be a possible hydrogen bonding, intermolecular hydrogen bonding. But in case of the 4, as they are far apart from each other, so the hydrogen bonding is not possible. So it can easily release a proton from the NH3 group. So 4 has the less pK value, and 4 is more acidic. Okay. So option C is the right answer.
Sir, sir, may I ask you some questions, sir?
Yes, sure. Who it is?
Sir, sir, I'm Priya, sir.
Yeah, yeah, sure.
Sir, actually, I'm asking it from the previous assignment. It's not from this assignment. If you allow me, then I will ask.
Actually, regarding previous assignment, we will discuss at the end of this session. Okay.
Okay, sir. Okay.
Let us
Completely
first
fine.
complete today's discussion. Okay. So let's. So it is regarding the cyclohexane 1,2 diol. Okay. So in case of the, let's first draw the. It is saying let's first draw cis and trans isomer separately. Okay, so this is cis isomer. So in cis isomer, one is equatorial and one is axial. OH groups are there. And in case of the trans isomer, it can have both the conformation, that is di-equatorial and di-axial. Okay, so both are trans and this is cis. So now tell me regarding dipole moment, which conformer will have the more dipole moment? In case of the cis one, exactly the cis one will have the more dipole moment, right? As one is axial and one is equatorial one, so the resultant will there. But in case of the trans isomer, can you please mute your system? Okay, so one will act in the this position and the another will act in the this position. So there will be net resultant dipole moment will be 0. Okay, so the cis isomer will has the more dipole moment, but in case of the option A, it is saying the dipole moment of the cis isomer is lesser than the trans isomer, so it is not correct, right? Okay, so it is saying that the intermolecular hydrogen bonding is stronger in the trans diastereomer. So in case of the trans diastereomer, you can see that the OH group are in the far apart from the each other. Okay, so there is least possibility of the hydrogen bonding as they are far apart from each other. Okay, and due to the to relieve the dipole-dipole repulsion, the trans isomer predominantly stays in the axial form. This form is predominant. Okay, so this is also not right. And
Sir, one doubt, sir.
yes, yes,
Sir, in trans isomer, if two OH groups are in equatorial position,
hmm,
so there is a possibility of hydrogen bonding, sir.
there is possibility of the hydrogen bonding, but due to the dipole-dipole repulsion, as you can see, the dihedral angle here is 60 degree. So there is a strong dipole repulsion. So they don't, in equilibrium, they don't stay at the di-equatorial form.
Sir, I'm not satisfied, sir. Sir,
In
in two OH groups are in equatorial position. Okay,
yes,
in trans conformer.
yes, yes,
Okay, so that means one OH is 60 degrees. Dihedral angle between two
60
OH
degree.
groups are 60 degrees.
Yes, yes,
So there is a hydrogen. There is a possibility of hydrogen, sir. They make
yes.
one hydrogen bond between two OH groups.
There is possibility of hydrogen bonding, but in case there is also a dipole-dipole repulsion between the two OH groups. To
Okay,
minimize that,
but
yes,
sir.
your point is right.
Okay.
If they are in cis position, dihedral angle 60 degree, there is possibility of hydrogen bonding. Okay,
Sir.
so to minimize that dipole-dipole repulsion, they predominantly exist in the this diaxial form.
Hmm.
Okay, so as you can see in diaxial form, there is no possibility of the hydrogen bonding.
Hmm.
So that is why in trans isomer, there is no intermolecular hydrogen bonding is possible. And in case of the C, it is saying that the cis diastereomers predominantly exist in the both form. This is also not true. The both form, a compound exists in the both form when there is some 1,4 position it is substituted. Suppose here is this OH and here some C double H group is there, then it forms some kind of lactone to stabilize the structure. But here it is 1,2 substituted, so there is no question of the both form arises. But in case of the option D, in the IR spectra, the cis diastereomer shows lower OH stretching frequency than the trans isomer. So in case of the cis isomer, as we can see that OH groups are closer to each other. So there is a possibility of the OH bond between the two hydroxyl group. And as we can see, when there is some hydrogen bonding, the IR stretching frequency of the OH bond decreases. Okay, so in case of the cis isomer, some intermolecular hydrogen bonding is there, and due to that, the OH stretching frequency of the OH group is decreasing. So option D is the correct one. So now let's move to the next question, that is question number 7. It is saying that on average at 30 Kelvin, there is 1 out of 1,000 molecules present in the twist-port conformation for cyclohexane, right? Although the twist-port is disymmetric and hence optically active, yet cyclohexane is optically inactive. Which of the following reasons may be responsible for this conversion? Okay, so the right option is B. As a twist port form, it is chiral one, and as you know that the inversion of the cyclohexane passes through this structure, like twist port, then boat, then another twist port structure. But as we know that these two twist port are the mirror image of each other, though they are the disymmetric one, but optical rotation of the one molecule is cancelling out the optical rotation of the another one. By flipping through the both conformation, one is converted to the another. So it is a racemic mixture, and it is optically inactive overall populations. Okay, so the correct option is option D. Okay, so now let's three conformations, three various substituted 1, 2 and 1, 3 substituted cyclohexane is given, and we have to say that which one have the how many gauge butane interaction. So let's draw first. So let's draw the first structure A. Okay, so it is 1, 2. So tell me how many gauge butane interactions are there? Methyl groups are far apart from each other. Is there any gauge butane interaction? With respect to cyclohexane, means we have to state the extra gauge butane interaction for the structure. So how many interactions are there? Gauge butane interaction?
0.
0, exactly. So it has 0 gauge butane interaction in case of the S. So let's draw the structure of the T. So one is axial and one is equatorial. So how many interactions are there? There are 2 interactions. Okay, 2 gauge butane interactions are there. And in case of the U, one is here, CH3, another is equatorial, axial hydrogen. So here overall one is here, one is here, and another is here. This methyl and this methyl. When we draw the Newman projection, the dihedral angle between these two methyls are the 60 degree. Okay, so overall 3 Gauss butane interactions are there. So the option D is the right one.
So,
Yes.
so as I read somewhere in the net only, in YouTube only, that cyclohexane has annular Gauss butane, homoannular Gauss butane interaction. So it actually doesn't have any physical significance. But in the last assignment, there was a question that that how many that cyclohexane has 6 Gauss butane interactions.
There are
So
6 Gauss butane. Actually, here what happens? Let me draw that. Right, all are there. Hydrogen is present. When we suppose all are the symmetrical, so there is no directional effect. So between the CH2 groups, as we know that in case of the Gauss butane interaction, there is some methyl-methyl interaction. But here, in case of the cyclohexane, between the CH2, through the every bond, between CH2 and the other group, there are some interactions. So it is considered as the Gauss butane interaction. So the 6 bonds are possible. So through the 6 possible bonds, there are 6 Gauss butane interactions in the cyclohexane. In case of as you were saying, that homoannular, but they are not so significant. But here we have to describe that it is written that with respect to cyclohexane chair form, how many extra interaction we are facing. Means here that 6 is already present, but due to presence of the methyl group, we have to state how many extra interactions we are facing. As here no sir.
Sir,
Sorry.
one doubt, sir.
Yes, yes.
Sir, in S conformer, we put two methyl groups in equatorial positions. So if you change the equatorial positions into two axial positions at 1, 3 positions, so
Mm.
we can expect more Gaussian butane interactions, sir. Can we expect?
Yes, we can expect it.
So when the methyl groups are at axial positions, two methyl groups, 1, 3 position.
Mm. But as we know that the methyl groups in the axial position is the most stable. Sorry, equatorial.
Uh,
Equatorial. So we have placed it in the equatorial position, the most stable one.
okay.
Okay. Okay. So that is why we are considering the interaction with respect to cyclohexane chair form. Means how many extra interaction we have. Right. Here the parent interactions of the cyclohexanes are present. But here we are trying to describe that how many extra methyl-methyl interaction, Gauss butane interactions is present in these molecules. Okay. So let's move to the next question. Question number 9. So it is saying that the 1,2-dibromocyclohexane, right? So we have to identify the incorrect statement. So it is similar to that of the which I discussed earlier, na, 1,2-di cyclohexane diol, right? So in case of the cis isomer, we have one axial and the one equatorial form. So like this way, we also have. This is cis isomer or trans isomer?
cis isomer.
Cis isomer. And the trans isomer can exist either both axial or both equatorial, right? So the percentage of the di-equatorial form of the trans diastereomer increases with the increase in the solvent polarity. Yes, this is true. As there is the dipole-dipole repulsion between the two bromine group, bromine also has some significant. Can you please mute yourself? Yes, so in case of the di-equatorial conformation, as there is a dipole-dipole repulsion between the two bromine atom, so there is a dipole. When there is increase in the solvent polarity, it also increases in the conformation. So in the gaseous state, whenever it is 95, and this is as the 5, but in case of the solvent polarity increases, it comes around 50-50, nearly around 50-50 population. So this statement is correct. So in case of the second, we are getting that the dipole moment of the cis diastereomer is more than the trans diastereomer. So is this true or false?
It
Here
is
it
true,
has.
sir.
Yes, it is true. Here it has the significant dipole moment, but in case of the trans diastereomer, it has the very low or zero dipole moment, as they are oppositely directed towards each other. So in case of the option D, we are getting the diequatorial form of the dipole moment is destabilized by dipole-dipole repulsion. It is true or false? I have already said.
True.
So, in
Yes.
the trans second one, there is that is also trans according to you, na sir?
This
So,
one.
yes, sir.
Oh, yes, yes,
So, this one also have dipole movement, sir. So, it
yes.
will be significantly low, or it will be low comparison to cis diastereomer.
No, as I have already discussed in the last question, in case of the there is a dipole-dipole interaction in case of the di-equatorial form, right? They are in the cis, both are equatorial, so there is a dipole-dipole interaction. The dihedral angle is 60 degree. So the trans isomer considerably states in this form, diaxial form. This the percentage of the this one is very low. Okay. So that is why
Yes,
in
sir.
case of the trans isomer, we are considering the only diaxial form, as the population of this form is significantly high. Yes, if this form has dipole moment, definitely. They are this one is directed this form and this one is directed in this form. They definitely have a significant dipole moment, but due to the repulsion of these dipoles, the di-equatorial form is very unstable. Okay, so the trans isomer does not stays in this di-equatorial form. Okay.
Yes, sir.
Okay. So now in case of the option C, what it is saying that at equilibrium, the trans diastereomer exists exclusively in di-equatorial form. Is this true or false? Hello?
No,
False,
sir.
false, sir.
Definitely
Also,
false. Definitely false.
False.
So this is the right option. Option C. This is the incorrect statement among the four. Okay, is there any doubt? If you want, I can explain again. Anybody has any doubt?
No doubt, sir. Proceed, sir.
Okay, thank you. So here it is saying that the which of the following is optically active but exists as the non-resolvable DL pair at the room temperature? So let's first draw the option of the A, which is sorry E means fast structure we are drawing. This is 1,2 substituted 1,2 dimethyl cyclohexane, and one is equatorial and the another is axial. Okay, so this is axial, hydrogen and equatorial. And if we flip the ring, and this is equivalent to this one. Okay, so if we consider this is and the 1 and this is as the 2, means it can has the either axial equatorial or equatorial axial form. So this is axial equatorial and it is equatorial axial. So they are enantiomer. Like, right? Can you see it? Actually, the same color. They are enantiomer. They are mirror image of the each other. What we have done, we have flipped the ring, flip-flop the ring, and got a 120-degree rotation through the vertical axis. Imaginary a vertical axis is there. We have flipped the ring, the upside will be down, and then we got the rotation, and we got after the rotation we got this structure, and this structure and this structure are the enantiomer of the each other. Okay, so they are two energetically equivalent chair conformations are there, that is axial equatorial and equatorial axial. They are chiral, non-superimposable mirror image. Okay, but at the normal temperature, the one is convertible to the another. As I have said that we have flipped the ring and gave a rotation, the first structure becomes the second structure. So as they are also enantiomer of each other, like they have some optical rotation, but due to the very easily they are convertible to each other at the room temperature, they are non-resolvable. They are non-resolvable to each other. So that is why the option E is the right answer. If we draw the another structures, then you will get some resolvable DL pair. Some will be meso compound, like this one. There will be a sigma plane. If we draw this in the chair conformation, there passes a sigma plane. So this is not optically active. And in case of the other, they are resolvable pair. But we have to find out here non-resolvable DL pair. So compound 1 and the compound 2 are though optically active, but they are interconvertible between each other at the room temperature. That is why we are getting a non-resolvable DL pair. Okay?
So,
Yes?
so it's mandatory that if some structure which is existing after flipping in an enantiomeric pair, then
Hmm.
they will be non-resolvable in the room temperature.
No, not necessary. In case of the one to this particular structure, we are getting this. We have to check this. Okay, after flipping whether we are getting the same or not. Like here in this case, the sigma plane is there, so we cannot give them a rotation. They are optically inactive. We have to check that. Not necessarily for in each and every case they will be non-resolvable DL pair will be there.
So how is it not resolvable in the option G structure?
Option G structure.
Yes, sir.
means option G structure, we are not getting, we have drawn one structure and another is the mirror image of the each other, but here the main point is by rotating this structure, the mirror image of the one, sorry, the flipped structure of the one, we are getting its enantiomer. This is not possible in case of the three. They are resolvable DL pair, but there is a structure and the mirror image of the structure is the another one. But here we are saying that from this one we are flipping the structure and by resolving the structure we are getting this one. Okay, so this is depends on the specific structure relationship, means in case of the 1 2 die substituted we are getting this one, but here our question state that non-resolvable. This is the most important part. You may get a 2 enantiomer. In case of the G you will get 2 enantiomer, but they are resolvable. Usually enantiomers are resolvable, non-superimposable mirror image of the each other, right? They are non-superimposable, but by rotation we are getting one structure to another. So there is a low energy barrier between the transformation of these two structure. That is why we are getting the non-resolvable dual pair.
So that means, according to you, you are saying that G will also have an enantiomeric pair, and it will
Yes,
also exist in enantiomeric pair. Then, what is the difference between these two? So this is also existing in an enantiomeric pair.
yes,
The
but
option
this
one.
term is also there, non-resolvable. Usually enantiomers are resolvable, right? If a racemic mixture
So
is there, there is some separating agent, as we know some. If it is an acid, we can make a complex with the base to separate them. But in case of here, it is saying that why it is non-resolvable. If it is a normal mirror image of the each other, they are non-resolvable DL pair. But here we are not doing any kind of that operation. We are just flipping the ring, this one, and we are giving it rotation. After giving rotation, it is giving the enantiomer of the first structure. Okay, that is
So
why.
I got you, sir. Actually, I got that. Even when we make the structure of G and we will it when we will convert it and flip it, then also you are saying that we will get enantiomers, right, sir?
Yes, yes,
Now, what I'm asking is that this to solve this question, we will require prior knowledge that this structure is non-resolvable. We can't solve it from this kind of solutions. Like if we know practically after doing that it is existing in the enantiomeric pair, then we will actually get confused at how to solve, how to make it actually say that yes, E will have is the right answer. But
yes.
what I'm
Actually,
saying is
you
that it is an experimental thing which we should be knowing as a fact, I guess.
not but you have to check this, means with the practice and practice you have to consider and check it by seeing the answer. Means if we are flipping and then we are giving rotation, you will not get the same structure in case of the G. Okay, so we have to do it, means practice it and check it whether it is giving or not. Sometimes it is experimental also, means what kind of structures we are getting. That is also experimental fact also is given there.
Sir, hello, sir.
Yes,
Sir, in case of G option, so two isomers are not interconvertible, sir.
no,
So in case of E, so these two are quickly
yes,
interconvertible. So
yes,
that's
yes,
why
yes,
we
yes,
cannot
yes.
we cannot
Resolve
resolve.
them. Yeah,
Yes,
exactly.
yes. So that is the reason,
That is the reason. Yes,
exact reason.
yes. So the
So
one at the normal temperature, means at room temperature, it is converted to the two.
yes, so there is always a dynamic equilibrium between these two enantiomers, these two
Yes, yes,
forms.
yes, yes.
Okay.
And this is only possible, we are getting this just flipping this structure and by giving 120-degree rotation we are getting this structure, but
Yeah,
this
yeah.
is the only we are putting the flipping and rotation, we are getting the structure 2. and 1 and 2 are the enantiomer pair of the each other, but they are non-resolvable. Okay, at ordinary temperature, they are interconvertible at ordinary temperature.
Sir, can we resolve them at so low temperature, sir?
Yeah, that is experimental. You may resolve it, but in case of the room temperature, as our concern, at room temperature in question is it is also given that at room temperature 25 degrees centigrade, so that is sufficient energy to flip flop the ring and give a rotation around the vertical axis.
Okay. Thank you,
Yeah.
sir.
Okay.
So actually, I have a request. If you can actually draw the structure of G and actually see that whether it is actually an enantiomer or not, and what is actually it's coming up after resolving it. Because the thing what he said, Ankit, who said, I don't remember the name. He said that it is a dynamic equilibrium existing between them in the room temperature. And
Yes.
it's actually what is like, we don't know that which structure is actually existing in a room
Okay,
temperature and
okay.
dynamic
No,
temperature.
you don't need to remember whether it is at room temperature or it is interconvertibility. We are getting the structure 2 only by flipping and giving rotation of the structure 1. In case of the structure G, you will not. They are just mirror image enantiomer of the each other. Okay. So question is put in such a way that you have to know some prior idea or experimental factor. That is why we are not, okay, forget about the room temperature and interconvertibility between each other. We are just drawing this one. We are just flip flop is a normal phenomena, as we know that the chair form of the cyclohexane, and usually they are in the dynamic equilibrium, as that we know, right?
Yes, sir.
There, if it's a C1 and this is 1C, this structure, so there is a possible pathway of the transformation of the each other, chiral C2 pathway and the sigma pathway. There are certain diagrams intermediate, so they are interconvertible within each other, that we know.
Yes, sir.
Okay, on you just remember that one, that by flip-flopping we are getting this structure, and only by rotation is also allowed. By rotation we are not supposed to get another structural conformation. So just by giving a rotation we are getting the structure 2, and eventually structure 1 from where we started and the structure 2 are the mirror image of the each other. But as here that flip-flop is involved, as here flip-flop is involved, and we are getting the structure 2 by rotating the flip-flop structure of the structure 1.
Okay, sir, I got it.
Okay. Okay, so now let's move to the last question, that is 9 methyl decaling system. So let's draw first the trans isomer. And here, as if the trans is the ones is upward and the another junction is downward in case of the trans decaling, and in case of the cis decaling, So tell me, how many interactions are there in case of the trans?
4, sir.
4, exactly. 1, 2, 3, and 4, right? 4 interactions are there. In case of cis-decalin, how many interactions are there?
Only 2.
No, not 2. One is here, one is this one is this one, 3, 4, and 5. Last time I also showed in case of the decalin system, how many interactions. There were 3, I think. There methyl was not there. So I think 3 were there in case of the only decalin system. But in case of the presence of the methyl, this extra with the methyl group, this extra Gauge butane interactions is there. So total it is 5. So what is the difference between cis and trans Gauge butane interaction? It is, sorry, it is 5 and it is 4. So what
One,
is
one,
difference?
one.
It is 1. Okay.
Yes, sir. So now can I ask the
Just
previous
okay.
assignment
Let's just
question?
stop today's discussion. Then we will talk about it. Okay. So any doubt from today's class? Okay. So now I am stop recording.
Sir?
Just a minute. 1 second.